Okay, section 1.3 is on page 27 in our book. Talks about rational exponents and radicals. Let me remind you really quick of what the principal radical is. Principal, like a principal, school principal. Principal radical is specifically the square root of a. That is always positive or 0, provided that there's a 2 sitting there. It's called the square root, the principal square root. So what do radicals do? Radicals undo exponents. That is, if I take 2 and I square it, I'll get a 4. If I take negative 2 and I square it, I'll get a 4. In that sense, if I was to ask, what's the square root of 4? Asking, what quantity did you multiply by itself? There's a 2 sitting there. That's why that's called the square root. Twice. What did you multiply by itself? Twice to really get a 4. Now the answer should be a positive 2 because 2 times 2 is a positive 4. Or it should be a negative 2 because negative 2 times negative 2 is a positive 4. But by what I just defined, you're never allowed to have a negative if you have a square root. And if I want to write the general rule, the nth root of a is always positive or 0 if the index, what's the index? If n is even. The index is really that value right there. That's something that we have to really worry about all throughout. In calculus, that gives students a hard time. We are reviewing, so I'm not going over this in full detail. If you were to take me for intermediate or beginning algebra, I would have spent way more time on that. Now, if I want to run a couple of examples just to demonstrate how this works, if I take, for example, the square root of 16, you would say, well, that's a positive 4, even though it is true that positive 4 times positive 4 is 16, and negative 4 times negative 4 is 16. But since this is a principal radical, it's a square root, the index is even, I can't have a negative. And if I look at the cube root of 8, well, what do you multiply by itself 3 times to get an 8? That's a 2. And if I look at the cube root of negative 8, you would say that's a negative 2 because negative 2 times negative 2 times negative 2 is a negative 8. So if the index is not even, you really don't have to worry about the positive or negative. It matches. Now, a couple of properties I need to show you. The nth root of a can be written as a to the 1 over n. Again, this is just a refresher. And similarly, the nth root of a to the m, I can write as a raised to the m over n. So the index of the radical is always in the denominator. But here, I have another way of writing this. I could say that's the nth root of a and raise that to the mth power. That is, I could say, but this is a to the 1 over n raised to the m power, and by this, so I could write it this way, and this turns out to be extremely useful. Now, I need to refresh your memory on how things work. You know, few of the rules, that is, if I take a raised to the n multiplied by a raised to the m, that's a to the n plus m. If I take a to the n and I raise that to the n power, these are exponential rules. Assumption is that you remember those, and if you don't, here they are. So we're not going to cover section 1.3 in full details. We're just going to pick few problems from the book and proceed for the rest. Now let me show you really quick. If I pick few problems based on the first property, if I look in my book on page 39, I'll notice that number 40, 42, 44. So, I'm going to do few problems. So the assumption is that you've seen that. I'm reviewing that with you. If not, here it is. I try to cover it in full details. So if I look at this, well, I have two options. I could either say this is the cube root of 8 to the 7th power, or I could say this is the cube root of 8 raised to the 7th power. And do we see that this benefits us a lot more? Why is that? Because I know what the cube root of 8 is. That's a 2. And 2 to the, I get carried away sometimes. 2 to the 7th, that's 2, 4, 8, 16, 32. 2, 4, 8, 16, 32, 64, 128. And the same deal here. I could say this is actually either the square root of 4 cubed, or I could say this is the square root of 4 cubed. Now you do get the same answer. That is, you could say 4 times 4 is 16 times 4 is 64, and that would be an 8. But imagine if you had to multiply 8 by itself 7 times first, how tough that would be. Instead, I could use this and say, wait a minute, that's a 2 cubed, and 2 to the 3rd power is actually an 8. Now, I do want to show one thing really quick. I do want to show that there's another way of doing this problem I'm not talking about. That is, you could say that as 2 squared, and you could say that's 2. When you multiply 2 times 2/3, that's cubed, which is an 8. The only reason I'm not mentioning that yet, because the outcome must be positive, and I don't want you to lose track that this is a square root. But of course, you could do that as well. And now that you've seen those, well, you know this is probably better off written as the 5th root of 32 squared. That is a 2 squared, and that is a 4. And let's look at the next problem. I look at these problems and I'm thinking, how am I going to work this out? Those don't have the same radical. That's very hard to do. Well, isn't that 5 to the 1/4? And wouldn't you say this is 5 to the 1/3? Wouldn't that be 5? And if I multiply 2 terms with the same base, don't you add the power? Wouldn't that be 1 over 4 plus 1 over 3? Isn't that 5 over 12? Wouldn't that be 3 plus 4, which is 7? Wouldn't you say this is the 12th root of 5 to the 7th power? Similarly with those, if I was to really think about what this means, this is the 4th root of m cubed times the 8th root of m to the 5th. So whenever you're multiplying and the index and the radicals don't match, you write it as a rational. And then you say, wait a minute, I know what that is. That is m to the 3/4 plus 5/8. That is m. And what is that? If you multiply by 2 top and bottom, now they're over 8. That is 6 plus 5. Wouldn't that be the 8th root of m to the 11? And in this case, 8 of those clear the radical as 1. And what's left underneath the radical? So this is saying this is m to the 8 times m cubed. Now keep in mind, I will have an issue with leaving an m because this is an even index radical, except here they say assume all variables represent positive numbers. So that never comes up, and that's something, you know, if it was up to me, I would actually have it come up so you don't suffer with that as much in calculus. And now let me look at some more examples, and we're gonna look at numbers 66 for starters. 66, if I glance at that and I'm thinking, okay, everything's multiplied, that's good. Cube root, what do you multiply by itself 3 times to get 27? That'll be 3. 3 divides 9, how many times? 3 times. And 3 divides, well, b is one of a kind, because there's only one of them, that's not enough. And 3 divides 24 8 times. And what's left underneath the radical? The cube root specifically. Just the b in this case. And that would be my answer, and that's pretty much it. If I look at number 64, I notice that there is no perfect square there. There isn't a number that I multiply by itself, an integer, that gives me 28. So what I do, I have to kind of like play around and say, okay, well, that is really 4 times 7. This is a perfect even number. This here I could write as r squared times r, and pretty much I could say, well, the square root of 4 is a 2. I have a 7 left over. The square root of p to the 8, or 2 divides 8 4 times. That's done. Q is one of a kind. And this clears the radical as 1. What's left underneath the radical? A 7, a Q, and an R. And if I look at number 68, the same deal happens. 275. I would know that, actually, let me think what that is. 25 times 11. So I could say that clears the radical as 5. 2, which is the index, divide 4 2 times. T is one of a kind. 2 divides 9 4 times, and I have a 1 left over from that. T I didn't touch, and 11 in there. So radicals are somewhat annoying to students, I know, but they never go away. Here I could do this a couple of ways. I could combine all of these under a single radical if they all match. And pretty much that's 40 x to the 8 y cubed a z over 5 x squared. Y times y is y cubed, and z times z cubed is z to the 4. And I could say that is 5 divides 40 8 times. 2 divides 8, x to the 8 divided by x to the second. 8 minus 2 is 6. Those cancel out, and I have a z cubed left over. And wouldn't that be 2? 3 divides 6 2 times, and 3 divides 3 1 time, and that would be my final answer. And if I glance at number 72, I could do the same deal. I could say, wait a minute, that's the square root. 36 divide 7 2 times. One of those cancel with none of those. I have 4 left. The b's is one of a kind. C, one of those cancel one of those. You have 6 left. And oops, I went for the wrong thing. I'm sorry. I meant one of those cancel one of those. You have 3 left. So I have b to the 7 and c to the 3rd. And wouldn't that be 2 divides 7 3 times, there's 1 left over, and 2 divides 3 1 time, there's 1 left over. Here I have an a b, and a square root of 2b. Timeout. Oh, I didn't pay attention to that part. Dang it. This 3 cancel those, and you have 4 left over. So that alters the answer really quick. That becomes b to the 4th, right? And there's no b on the bottom. Oh, how did that slip my mind? Wow, that's odd. I didn't even see that coming. So let me clear now. That's gonna be bc, b squared c, and a c left over. And this is gonna be a times the square root of 2. And if I rationalize, multiply by square root of 2 top and bottom, I will end up with b squared c, the square root of 2c, and these radicals clear, and I'll get a 2a. And that would be my final answer. And let me give you the homework on this. And there's the homework for this section. Page 39, number 39 to 45 odd, and 63 to 70.